This presentation is about resonance, and resonance is something that keeps coming up in every chapter in all organic chemistry. So somewhere or the other, you're going to come across resonance. So it's covered early, but it doesn't mean you have to master it early. Okay, you can take your time a little bit to learn it. So what is resonance itself? So first of all, there are many molecules that can be represented by more than one structure. Not all molecules, and that's the whole point about learning resonance, is that which molecules are going to show resonance. The other thing about resonance, it's only on paper. Okay, so you cannot pick out a resonance structure from a solution and say, okay, I have this resonance structure, so I can prove it's there. The only way you can tell that you have resonance is by studying the kind of products you get in a reaction. Okay, so resonance right now, it's only on paper. We will just show the structures because, there are conditions about writing those kind of structures out. Okay, why so? Because and why I study the products also, and that is because there are some structures which contribute a little bit more than the other. All right, because there is some structures that are more stable than the others. So when you write all these structures, we are able to predict whether the structure is going to be stable or not, which means is it contributing to the stability of resonance, okay, or the molecule itself. Then you can take all these resonance structures and draw what is called a hybrid of the structure. What the hybrid will show is the delocalization of electrons that's going on. So in some cases, the delocalization is over 2 or 3 atoms. In some cases, the delocalization is over more atoms, 6, 7, maybe. So depending on what kind of bonding you have, what kind of heteroatoms you have, all of those things will determine how your hybrid looks like, okay, or how many structures you have. That will show how many what kind of a hybrid you have. So then the more contributing structures you have, which means that any structure that contributes to the stability, then the molecule itself is going to be resonance stabilized, okay, which means that it's a stable structure. When resonance structures are stable in a certain way, then they give different kinds of product. If they're not, they give different kinds of products. So when we are learning about reactions in future and we talk about resonance, that okay, this structure has a resonance structure, it will have different kinds of products. Okay, it's possible. So you have to be ready for that also. When we write the resonance structure, we are going to start learning about curved arrows, and curved arrows are written out to show movement of electrons. Okay, so that's another thing that is key for showing resonance structures.
Okay, going on. The energy of the actual molecule then is going to be lower than the energy of all single contributing forms, which means that by the time you get to the hybrid, it should be very low in energy, or it should be nice and stable in energy. So it's not really a rule, it's one of the outcomes, okay, of drawing resonance structures. If you have two equal resonance structures, then they will make equal contribution. Okay, so we will talk a little bit about what makes an unequal one, but otherwise, most times, if they're equal resonance structures, they will contribute equally. So, for example, right here in the benzene, if you look at the structure here, this has a double bond, single bond, double bond, single bond, double bond, single bond, alternate double bond and single bond. And you can move the double bonds to a different location, but it essentially looks the same as this one. So which means that both of them are contributing equally, all right, to the final resonance structure. So this is the final representation of the hybrid structure for benzene. The unequal resonance structures contribute based on their relative stabilities, okay, which means that if a structure is more stable, it contributes more. If it is less stable, it will contribute less. So what is a more stable structure? Okay, so let's look at the stability over here. The stability depends on, first of all, the total number of covalent bonds. The more covalent bonds there are, the more stable a contributing structure is. What does it mean by covalent bonds? It means it is the electrons are bonded rather than in form of a charge, like a positive or a negative. Okay, so this structure here is going to be more stable than structure number 7 or 8. Even though 7 and 8 are equally fine, they're okay resonance structures, they are writable, they're not wrong, but they're not stable. Okay, and so they don't contribute much. And again, why are they not stable? It's because of this charge distribution that we have here. In the case of 6, all the electrons are bonded. So this is a lot more stable structure for this compound. And then here, the ones that are not contributing very well for resonance structure is one in which case there is a charge. Okay, and which atom can take a charge better is an important thing. So for example, more electronegative elements will take the negative charge better, more electropositive will take the positive charge better. And in this case over here, carbon is not a very happy camper, but here in this case, in this structure number 10, carbon is happier. Okay, and so it's really important that all atoms be more stable. Okay, oxygen is still stable over here and it is stable here also, but carbon was not stable in 9, but carbon is more stable in 10 because of the octet. Okay. And then in these cases where separation of charge happens, which we saw in the previous slide also, whenever there is a charge separation, those structures are not very good structures. Okay, again, because of the number of bonds present. Okay, in this case, 11 is going to be a lot more contributing structure than structure number 12. And again, this is what I was saying to you before, is that negative charges should be more on the electronegative elements. So for example, an oxygen can carry the negative charge a lot better than carbon can. So that structure will be preferred over. Okay, and so the positive should be on the less electronegative atom, which means carbon can carry the positive better, not the negative. Okay, and so that's how you decide which structure is going to contribute more or less to. Let's look at an example over here for nitrate ion. The nitrate ion has nitrogen in the middle and has 3 oxygens. Nitrate ion is NO3 minus. Okay, and if you look at the total charge here, there is 1 positive on nitrogen and 2 negative oxygens, so the total charge is -1. You can calculate the formal charges on each of these. That's how we came up with these charges, and that's why you need to learn the formal charges as well, so you know where to put the positive and the negatives. But anyhow, writing the resonance structure for this. So once you start with one structure, now you can start moving the electrons around. How do you move them? You look at where you have the electrons. So here, oxygen has the electrons because oxygen is negatively charged. You can start from this oxygen or this one. It doesn't really matter because these 2 oxygens are equal. This oxygen is different because it has a double bond. These 2 oxygens are different because they have an extra electron. So you can start the resonance structure from this oxygen or this one. It doesn't matter. So we started with this one here. And the electron pair is coming down to the bond. But because it's coming down to the bond, nitrogen is going to have more electrons that it can hold, and therefore the electrons from nitrogen oxygen double bond are going to move to oxygen over here. Now remember, a bond is a pair of electrons, and then here also we are moving a pair of electrons. So the final structure then is a pair of electrons here, which is resulting in a bond, and those pair of electrons actually move right here to oxygen. Oxygen has 2 lone pair of electrons here and 3 lone pair of electrons here, which results in an excess of 1 electron. Now you can take electrons from this oxygen, move them to this bond over here, and then now this double bond will go right back there. And so you get a double bond here and a negative charge back there again. So at any given time, there is 1 double bonded oxygen in any of these structures and 2 single bonded oxygen, okay, in these structures. When you look at these structures, you might think, hey, they all look alike, okay, and that is true. In this case, they do all look alike, okay, in case of the nitrate ion. In some of the small molecules, The structures look alike, which means that all of those structures are equally contributing because they're all alike. Okay, and so it doesn't matter. That's not our problem. If we can move the electrons around, then it's fine. And if all structures are all contributing, that is fine also. All right, so don't worry about that. They all look alike. So long the electrons are moving, okay, that's what makes a new resonance structure. This final structure over here shows the hybrid, okay, of the nitrate ion. This is a 2/3 negative charge. This is a 2/3 negative charge, 2/3 negative charge. And look at this dotted line, okay. All of this means, first of all, that the oxygen does not have a complete negative. And the second thing is that the bond between oxygen and nitrogen is not quite really a double bond. And that is because these electrons here during resonance are moving so fast that the bond doesn't really know whether it is a single bond or a double bond. So the switch is so fast that the bond is kind of an intermediate between a single and a double bond, which means that the bond is an average of the bond length for nitrogen and oxygen, okay, which means that it is an average of the single bond and a double bond in the final hybrid structure. The two things that are important for resonance and how we know that resonance actually exists is one of this fact, okay, about the bond length. The bond length for nitrate ion is between a single bond and a double bond. That tells us that there is something else going on, because if it was just simply a nitrate ion with two single bonds and a double bond, then we will have two different bond lengths for this molecule, for this ion, but we don't have that. We have a single bond length for all of these bonds, and that indicates that there is something else going on, which is why we can come up with something like resonance in which electrons are moving. Otherwise, there is no resonance, okay, which means in that case we should see the two single bonds and double bonds, but because we are not seeing that, we know something else is going on. And it has shown that all three bonds are equal in length, which means that the electrons are equally distributed. That's number one. Number two, the thing is that the bond energy of these bonds are alike. Again, if you have a single bond and a double bond, you'll have different bond energy. A double bond is stronger than a single bond, and therefore it will be harder to break. But it's seen that the nitrate ion, they have all the same bond energy, which means that there is something else going on, which is called resonance. Okay, and so we have the average of the double bonds and single bond that's going on for bond length, and then of course the bond energy, which kind of verifies for on. Here are some more examples for resonance, and again, note the arrows, okay, and note the arrows as in they're all double-headed arrows. They are curved arrows. The curved arrows indicate transfer of electrons, and we will talk about this in organic chemistry and discuss all the different kind of arrows that we have. And again, you can see the movement over here from a double bond to the oxygen, and then the transfer of these lone pair of electrons to this bond over here. So the final structure you end up getting is a double bond between this, because the carbon and oxygen, because that's where the electrons moved, and the electrons from here had moved to this oxygen, so it has now excess of electrons. This curved arrow here again shows movement of electrons, and I want to point out that this electron here, this arrow over here is a double-headed arrow, and this is what is shown for resonance. Please remember, this is not the same arrow as equilibrium, okay? So you cannot draw the same arrow. This is the arrow for resonance, and when we draw this arrow, it indicates to us that these are resonance structures. In case of equilibrium, you really have an equilibrium where you can push things forward and backward, okay, as in a reaction, but this is not something like that, okay? All right, the carbonate ion will be the same as the nitrate ion because you can see the movement of electrons all over the place. So the hybrid will be where you have a carbon with a partial double bond and single bond between the carbon and oxygen, okay? And then the negative charge is distributed all over the three atoms, okay, of oxygen. All right, and here is acetone, and if we add base to it, you create a charge distribution. That's not the important part. The important part is that if there is excess electrons on carbon, now we can move those electrons to here, and the electrons from this double bond can move on to the oxygen. Why do they move to oxygen and not to not these electrons to carbon? Well, first of all, oxygen is more electronegative. That's why electrons will move to oxygen. And the second thing is that this is where the double bond is. So that's where the electrons are going to move from. Okay, so you cannot move the electrons from here to say this carbon. Okay, so move them to the more electronegative element, move them from double bonds, move them from negative charges, or as it was here also in the negative charge. That's how you would move it. Okay, so this is for acetone, and again, once you move these electrons here between carbon-carbon, you get a double bond here. These electrons had moved to the oxygen, so you get a negative charge over here. The hybrid for this structure would be that you have the single bond and then you have a dotted line here between carbon and oxygen, and then this carbon and this carbon. That would be the hybrid.
On this slide, I have two examples for us, okay, to work on, and the two examples are going to be one for a cation and one for an anion, because I want to show you how to move these electrons and how to write these resonance structures. So let's start with the top one, which is a cation. I want you to keep an eye on how I am moving my electrons and in which direction I'm moving them. So for the first one, which is a cation, this cation right here, I'm going to move the electrons towards the cation. Why towards the cation? Because a cation is electron poor. So I can move only electrons towards the electron poor. I cannot move electrons away from electron poor. Now, since I'm moving the electrons from here to here, this carbon automatically now will be electron poor because I have moved electron from this double bond to this single bond here. Now please remember that the electrons we are moving here automatically will be the pi bond. We cannot move sigma bonds. Which one is a sigma, which one is a pi, it doesn't matter. It's the double bond, okay, that's moving. Which means if it is a single bond, you actually cannot move that single bond, okay? So if there was no double bond there, I will not be able to move any electrons from there, okay? So you can move only double bonds, triple bonds, lone pair of electrons, wherever there is electron density. If there is none, you can't move electrons. Okay, so here we have the double bond here, the charge, then the positive charge comes over here. I still have the double bonds on the carbons here. So that's still there. So now I can move these electrons over here. So then automatically what happens is that this carbon will become positive because now that will have low electron density. I like going down and around in a circle, so this is how I'm going. Feel free to follow my lead. If not, you can come and start writing from here also, okay? It's entirely up to you. This is how my habit is. So then my positive is here and I still have the double bond. Hopefully you're getting the idea of what we are doing now. So we'll move these electrons here towards the cation, and these double bonds are still there. The double bond is shifted here now, and now this carbon is going to become electron poor. So these are all the structures that we can draw. We can't move this charge anymore. If we do, we start going back, which is really what resonance does. Okay, so it'll start going backward. Now to write the hybrid for this structure, it would be this. We started from this carbon, we went all the way to this carbon, taking this wonderful scenic route. So that's what we are going to do now also, is going to start from this carbon, and let me get the color of my pen correct. Here we go. All the way here, all the way here, 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 here. And what charge did we distribute? The delocalization was for the positive charge, okay? So that is your hybrid. So the hybrid shows that the charge was distributed all the way from the first carbon to the last carbon. Okay, now we're going to deal with the anion. The anion is dealt with slightly differently than the cation. Why? Because the anion is electron rich. So if it's electron rich, you're not going to push electrons towards it. You're going to move electrons away from it, okay, because it is capable of giving electrons because it is electron rich. So if you move these electrons to this bond, now this carbon is going to have more electrons, which means that these electrons will shift to this carbon. You will notice that in the carbocation, I did not have to show how I got the carbocation because it was automatic. All these arrows show you that it was automatic. Okay, it happened because I moved electrons away. But in an anion, I actually have to show this movement, okay, to show that this is where the electrons are going. So now my new bond is here, my new charge is over here, and I have bond here, bond here. Okay, so now that I have a negative charge here, I can move this here, and this is going to move here. Why this is going to move? Again, it's a pi bond. So pi bonds, lone pair of electrons, they can move. So now the structure becomes this. So now I have a double bond here. My negative charge is here, and the double bond is here. Again, I hope you're getting the gist of this and you're getting more comfortable. And so now with this negative charge, I can go ahead and move this here and move these electrons to that carbon. So which means double bond here, negative charge here. That's it. That's how far I can go. All right, so now I'm going to go ahead and draw my hybrid. My hybrid will be kind of similar to the one that I had in the cation because the charge distribution is still the same, or I should say the delocalization is still the same, going all the way from here, all the way here, here to here, except now it's going to be a negative charge distribution. So these are the resonance structures for these organic molecules. Now, just let me mention about 2 or 3 things here before I move on. First of all the arrows are double-headed arrows, double-headed meaning this kind of a full arrow, and this full arrow means that you're moving a pair of electrons, okay? So the curved arrow here, it shows that you're moving a pair of electrons. Sorry about that. That was the wrong color. Okay, so here we go. Again. This curved arrow shows the highlighted one. It shows that you're moving a pair of electrons. Okay, so that's an important thing over here to note. The other thing I want you to note is this arrow. This arrow indicates that you have resonance structure. You cannot write the equilibrium arrow. Equilibrium arrow is this one, and that arrow doesn't work for resonance. Okay, so don't do that. And the next slide, I have all the arrows for you, so I'll go over that, okay, in just a minute. All these structures for the cation that I have drawn, all these ones from here to here, all of these are equally contributing. How are they equally contributing? Because they're very similar. The bonds are between carbon and carbon. The cation is on a carbon. So all structures are equally contributing. Not one is more than the other. Okay, so that's how these structures are drawn. There is more practice on videos. Okay, so if you want to take a look, you're most welcome to do that. Let's look at all the arrows that we have in organic chemistry, and we're very picky about our arrows, okay, in organic. So you have to be careful that you draw the right kind of arrow at the right place, okay? So the first one you already know, which is the synthesis arrow. Straightforward, you do that in Gen Chem. You learn about the equilibrium arrow also in Gen Chem. So in equilibrium arrow, things are going back and forth all the time. You just learned about the resonance arrow, which is a double-headed arrow in a different way. Not the equilibrium arrow. Equilibrium, you have 2 arrows. Okay, so resonance is just 1. This one is going to be a new one for you, and we will start using this later on when we start doing synthesis, because this is going backward. This is retrosynthesis. And in retrosynthesis, you actually work your way backward into a synthesis, and you will see the practicality of that when we get there, okay? Because usually when we do synthesis, we use this forward arrow, to show that we're going forward. But in organic, we have a tendency to start from the product and then go towards the reactant, okay? So we'll do that when we get there. But the retrosynthesis arrow, you cannot use this arrow to show synthesis, okay? You cannot, not at all. Then we started using the curved arrow, and the curved arrow is for transfer of 2 electrons, and the transfer of 2 electrons is shown by this double-headed arrow. Okay, so it's kind of a normal kind of an arrow, but we call it a double-headed arrow. And then here, this is the transfer of 1 electron, so you can see this is half-headed arrow. Okay, so that's transfer of 1 electron, which also we are going to do this semester. So what you should learn from this PowerPoint presentation here in this lecture is, of course, you should be able to write all the resonance structures out, be able to move electrons around, be able to identify structures that, okay, these two are resonance structures. And then using all those rules, okay, that I went through, that you can't move atoms, you can't move single bonds, things like that. So the rules of resonance becomes really important for us, okay? And so that's something you should be able to do. Learn how to use those arrows, the curved arrows. I want you to start getting comfortable with this because we're going to be using them a lot, okay, as we go on. Again, as I said, if you don't master it this time, all the resonance structures, it's okay. Take your time, you know, one step at a time, okay? We'll be fine.